All right, so power series is a topic that is covered in Cal 2 for the most part, but this is just a little quick recall of that information. So a power series is an infinite series centered at A if it follows this form right here. For example, if I had this as my power series meaning like x raised to the power of n, we would say that this is centered at a equals -1. Most of the time, what we're going to be looking at in our series is centered at a equals 0. For example, this one right here. Here is some important information as far as power series are concerned. A power series converges, meaning that it actually has a sum. An interval of convergence can be found, which is the set of all numbers in which x actually converges to that. You can find the radius of convergence then around the center. And if it converges for all x, then we say it converges absolutely. Anything within the absolute convergence interval, we say, or anything that it converges for in the interval, we say it converges for absolutely. Anything outside of that, we say it diverges. And if it is all real numbers, then we say it converges absolutely for all real numbers, okay? And then we use the ratio test in order to find all of this information. So this is where we are going to spend the most of our time. So this one wants me to find the interval and radius of convergence of our series, and we'll do that using the ratio test. So we will say the limit as n goes to infinity of the n plus 1 term, so x minus 3 to the n plus 1, over 2 to the n plus 1 times n plus 1. And then we're going to divide that by the nth term, or what you end up seeing in your expression for the summation piece. Now, we multiply by the reciprocal when we divide fractions. So you can write this as x minus 3 to the n plus 1 over 2 to the n plus 1 times n plus 1. And I'm going to multiply that by 2 to the n times n over x minus 3 to the n. And in order for this to be convergent, we need that limit to be less than 1. Let's look through this and see what things might cancel so that we can simplify this a little bit. Anything that has a base to the n plus 1 is the same as that thing to the n times that base to the 1, if we want to write it that way instead. So these terms would cancel out. 2 to the n plus 1 is 2 to the n times 2 to the 1. So those terms cancel out. These terms will not. So I'm going to take anything that doesn't have an n outside, keeping it in absolute values. So I have a 1/2 x minus 3 to the power of 1. And then inside my limit notation, I have n over n plus 1. And I need to know for what values that is less than 1. All right, well, 1/2, it doesn't matter what I have inside here. 1/2 can actually pull out of that absolute value bar. Oh, and this should be times, not equals. And then this limit, as n goes to infinity, actually gives me 1. If you remember from pre-cal, if you have the same power over the top and the bottom, and you're looking at end behavior or horizontal asymptotes, then when you have the same power in the top and the bottom, you look at the ratio of their coefficients to find that horizontal asymptote or that end behavior. And so this ends up being 1. is less than 1. That means x minus 3 must be less than 2 if I multiply the 2 over here. And if you notice back in the beginning, looking at our power series, I know I said we're normally going to look at a being 1, but this power series right here, x minus 3 means that this is centered at 3. So I want to make sure that I get that inequality down to that expression, because then that tells me my radius is 2. Okay, so my center is 3, and then my radius is 2 around that. Or we can also solve this algebraically using the compound inequality, -2 to 2. If I add 3, I get 1 to 5, which makes sense on my number line, like in the notes from the textbook. All right, the next piece is you do have to evaluate your endpoints to make sure if x is 1, do I actually have a convergent series when x equals 1? So let's go ahead and plug in x equals 1 and see what happens. All right, I end up getting -2 to the n in the top and 2 to the n in the bottom. Well, this would be the same as -1 to the n times 2 to the n over 2 to the n times n. So my 2 to the n's cancel, and I have an alternating harmonic series, so this does converge. So I do have a convergent series at x equals 1. Let's try 5. All right, when I plug in 5, I end up getting 2 to the n over 2 to the n times n. 1 over n, the harmonic series diverges. So this is going to be my interval right here.